Hello, welcome for the next topic. Today topic we are going to see about piezoelectric type accelerometer. Piezoelectric type accelerometer, it's used for measuring vibration. So already in the previous class we had a discussion on seismic type transducer. That seismic type of transducer is also used for measuring vibrations, and also we can measure the shock. So this piezoelectric type accelerometer, piezoelectric transducer will act like both sensor as well as actuator. So it will sense the phenomena as well as it will actuate the input of the signal. Whatever the signal we have in piezoelectric transducer, that will actuated through piezoelectric. And when you are concentrating on this piezoelectric crystal, we are having two different types of crystal. One is called natural and another one is called synthetic. You can just look at the diagram. Here we have a piezoelectric material. The material is, there are two different groups of materials we have. They are categorizing natural and synthetic. The natural groups are quartz, Rauchelia salt, ammonium dihydrate phosphate, as well as we have synthetic group ethylene diamine tartrate as well as lithium sulfate. But generally in piezoelectric crystal, the people used to go for quartz, because the quartz which is the one, it is giving a high sensitivity output voltage. So when you are applying a stress or the pressure to this particular piezoelectric material, automatically this will create an output voltage. The output voltage we can see across the voltmeter. So that is what here the diagram is shows. So how the piezoelectric transducer, here you have a piezoelectric transducer and applying force we have, and the output of this particular device transducer will be calculating across these two terminals. So when a force is applied to the piezoelectric transducer, it will create an electric field output voltage. So the output voltage is calculating across these two electrodes. So whenever the forces apply, automatically there will be a deformation. So the deformation is in terms of thickness, then width. So whatever the original thickness is T, and delta T, which is nothing but the change in distance. This is how piezoelectric transducer is working. When you are coming across this piezoelectric transducer, you can just look at the diagram. This is how, when you want to purchase a piezoelectric transducer, the devices look like this. So this is what the piezoelectric transducer, it consisting of some terminals. These lines were connected to the your whatever the vibration or whatever the shock you want to measure, that particular device will be connected to these three terminals of this particular transducer. So when you are coming across this piezoelectric accelerometer, there are different modes of operations. The modes of operation is like, if there is a deformation, it is in like in thickness, then it is thickness shear. If it is focused on the front post, then it is phase shear. Generally your crystal will give three deformation, that is roll, pitch as well as yaw. That is along x-axis, y-axis and the z-axis. So this is how the force displacement axis will happen in your piezoelectric crystal. And this is what called length as well as shear action. So these are the different types of modes of operation in piezoelectric transducer. So generally piezoelectric accelerometer, the people used to go for shear mode operation. Shear mode operation will give you a high sensitivity as well as it will give a larger movement for less energy. That is the reason shear mode operation is working. So the effect of stressing a piezo to generate a voltage is called direct piezo effect. So generally in piezo resistive transducer, there are two things they used to call inverse PEE as well as direct PEE. That means direct in the sense whatever the signals when you are applying, you will get mechanical, like when the pressure is applied, electric output voltage. If electric signal converting into mechanical, then it is called as an inverse effect. So this is how your electric accelerometer, which is, so this piezoelectric type of accelerometer will have piezo. Piezo in the sense it is nothing but press. That is what your piezo talks about. So this piezoelectric type accelerometer, which is used for measuring the shock. The piezoelectric crystals are acting as a sensor. So already I have explained what are the different types of materials we have. That is what I am given here, natural as well as synthetic one. So this is what the device we have. So this part across this is what your electrodes, and here we have a piezoelectric crystal, and the upper portion we have a mass, then clip type spring, then we have a moving and controlling. This is for spring type, and here which is moving and the controlling operation we have. Then this particular crystal which will be connected to the housing. So what will happen when the pressure or force is applied to the mass, automatically the crystal, there will be a deformation. So if a mechanical force or pressure which will apply to the particular piezoelectric crystal, then there will be a deformation. The deformation will be identified through this particular two terminal, that is what your electrode. You will get an output, that is E0. So this is how the operation is working. So the effect of stressing a piece to generate a voltage, which is called direct piezo effect. The inverse piezoelectric involves inducing a stress in the piezo element by applying an external electric field. So this is what your crystal, when a force is applied, then there will be a deformation, so it will generate a voltage. So the displacement of a mass can be measured using piezoelectric sensing element. So in present technology, this piezoelectric accelerometer, which is used in the embedded system concept. You all know in our mobile we are having an accelerometer. It's a sensor which is operating under the mobile. So whenever you want to go, you want to have a Google map, if there is an accelerometer, if the accelerometer is not present in your mobile system, you can't able to find out the Google map. Okay. So this is how in your accelerometer sensor there is an advanced technology, that is MEMS mechanism, and the sensor they have used is ADSL335. So this is, we have a spring and the fixed end and the moving end. So what will happen when a pressure is applied, that is when a vibration is applied, automatically between this particular portion, I mean the front and the back portion of this will be getting deformed. So this is how this particular accelerometer sensor is working. So this piezoelectric sensor, it is also used for quality assurance checking as well as process control application the people used to go for. So the charge produced is exactly proportional to the applied force and generating at a right angle to the force. The change is independent of the element size and the shape. This is what your shear mode operation. So here mechanical to electric and electric to mechanical, that is what direct piezoelectric as well as inverse piezoelectric effect. And what will be getting the output voltage Q, which is equal to D into F. So F is force, Q is electric field strength, and D is charge sensitivity. You all know force, which is mass into acceleration. So I am just replacing with, and moreover there are two electrodes. So the phenomena which is similar to your capacitance. So the crystal has its own capacitance. So the output E0, which is equal to Q divided by C. So when you are replacing this term with your previous line, so automatically you will have E0 which is equal to Q. I am just going to replace with the D into MA. So you will have E0 which is equal to DMA divided by C. So your output I am getting in terms of acceleration as well as your capacitance. So the output voltage is a measure of acceleration. That is what we got. So when you are coming across this crystal, I want to measure the vibration. How? So already we have an equation Q is dF. But I want to replace this force with related to Young's modulus. So what is F? That is F which is equal to area Young's modulus into del T by T. That is nothing but whatever the changes, whatever the deformation across the area as well as the thickness, as well as the width. So when you are talking of this particular term F, which is AE into del T by T, E is nothing but Young's modulus. Young's modulus is stress by strain. You all know stress is force by area and strain is nothing but change in deformation. And area, which is nothing but the multiplication of width as well as length. So I am just going to replace this particular term with this equation. So this Q is equal to dF, and I am getting some expression for F also. But whatever the equation I am going to write in terms of Q, I am just going to replace it with my E, that is my Young's modulus. So you will have D into AE by T into del T. So the same term I am just going to replace with, because already we have the expression E naught is Q by C. What is C? C is nothing but epsilon R epsilon naught into A by T. This is relative permittivity of the space as well as the air medium. So C, which is equal to epsilon R epsilon naught into A by T. So I am just replacing with this particular element with this particular expression. So we'll have E naught. Q is also already you got some expression. I am just going to replace this Q as well as C. So I will get E naught, which is equal to dFT divided by epsilon R epsilon naught into A. So force by area, that is F by A, that is nothing but your pressure, because you all know pressure, which is nothing but force by area. So this F by A I am going to replace with P. So what will have your field strength E naught, which is equal to D by epsilon R epsilon naught into T into P. So D by E R E naught I am just going to have G. What is G? It is voltage sensitivity of crystal. So after substituting this particular term, you will have E naught, which is G into TP. So your G, which is equal to E naught by TP. So E naught by T I am just going to take as a single term. So your E naught by T is epsilon. Epsilon, which is nothing but electric field strength. So finally, voltage sensitivity of a particular crystal G, which is nothing but epsilon by P. So your epsilon, which is nothing but electric field strength. So this electric field strength, which is calculated through E naught divided by small t, and P is nothing but your pressure. So the charge sensitivity D, which is equal to epsilon R T naught into E naught into G. So the charge permittivity of the quartz, which is nothing but 40.6 into 10 power minus 12, and charge sensitivity value is 50 into 10 power minus 3 voltmeter divided by Newton. So this is how your piezoelectric accelerometer is working. So the next one is about thermopile. Thermopile, which is also nothing but used to measure temperature, and this device is also used for measuring thermal radiation. So what is thermopile? Thermopile, which is nothing but a series connection of thermocouple, are called thermopile. You can just look at here. I am just going to have 3 thermocouples connected together, and there are 2 junctions created and 2 different metals I have used. One is gold and another one is manganese. So when you are connecting those things, and I am just going to give an incident on radiation, whatever the variation is going to happen across this particular junction, that will create a output voltage. So this particular electronic device, which convert thermal energy into electrical energy, that is what the operation of your thermopile. So thermopile, which is nothing but a thermal radiation device, it's a series connection of thermocouples, are called thermopile. It is also used for measuring temperature. Thank you. So I think you would have understand how piezoelectric accelerometer is working as well as thermopile is working. Okay.